We're going to continue on here. Last time we were talking chapter 9 and stoichiometry. And we really got into percent yield and limiting reagents. So remember, percent yield is the actual yield divided by the theoretical times 100%. As we talked about in most sort of book problems, you will be given usually this number here. The actual is usually given to you somewhere in there. It's the theoretical yield, which is your maximum yield that usually you need to calculate. And this is usually the one you have to calculate. Remember that you usually will do some type of stoichiometry problem, which could just be a basic stoichiometry problem, or it could be a limiting reagent type of stoichiometry problem. Remember that how you really know that you do have to determine the limiting reagent is usually you're given enough information for both reactants that you're able to get to moles. So that's really the key to know that, at some point you need to determine the limiting reagent. We talked about a few ways you could do that, but one way, again, is just the basic kind of 4 steps. You want to balance the equation. You want to convert whatever they give you into moles, which usually involves getting it to grams using the molar mass to go from grams to moles. You want to do the mole-to-mole relationship, which is the stoichiometry part. And then obviously you want to take those moles into some other unit. Once again, on the back end of the calculation, oftentimes we will go from moles back to grams, which also requires usually the molar mass to do so. Now, if you do have a sort of limiting reagent situation, one way that we talked about you could do it is basically these same steps, except right about here, you're going to do your limiting reagent calculation. And remember that you do need to do some type of calculation to determine which one's the limiting reagent. And in this method, basically what you do is you choose one reactant and you do a very simple little calculation to determine how much of the other reactant is necessary to use it all up. And then you basically compare to what you're starting with. And if you do have enough of that reagent to use up the other reactant, then that would be the excess reagent. If you figure out that you need more than what you're starting with, then that means that you do not have enough, and that would be your limiting reagent. Remember that it's always the limiting reagent that determines how much product you're going to produce. So once you do that calculation, once again, obviously you should continue the rest of the steps there with the starting amount of your limiting reagent. The other sort of common way that we talked about that people will do these type of problems is you could just do 2 separate stoichiometry calculations, one starting with one reactant and go to the product you're interested in and see how much you produce. The other calculation is starting with the other reactant that was given to you and going to the product, same product, and figure out how much you would produce. Whichever one produces the smaller amount of product is both for your limiting reagent and also your theoretical yield. So again, there's a few different ways you could actually do these type of problems. Any questions on that there? All right, so I think we skipped one, so we're going to go back to that one to wrap up this chapter here. We're going to look at this equation here, and we want to calculate the theoretical yield, our percent yield, I'm sorry, and theoretical yield. In kilograms, if we start with 2.46 times 10 to the 4 kilograms of TiCl4, molar mass 189.7 grams per mole for the periodic table, it's allowed to react with 1.44 times 10 to the 4 kilograms of magnesium, 2431 from the periodic table. What's the theoretical yield and percent yield if we actually did yield 5.42 times 10 to the 3 kilograms. So take a few moments there, see what you come up with. I think you might need TI here, which is 4788 on the periodic table. All right. Let's see. All right, so let's take a look at this. Remember, so stoichiometry type problem here, and obviously we have the starting amounts of both reactants. And that tells us, by the way, that it is a limiting reagent problem because I could definitely go to grams and then some moles of that guy. And I could do the exact same thing basically for that guy. So that's the key to know. This is a limiting reagent problem. They also here told us basically our actual yield, which is right there in this particular problem. So really in this case, we just need to solve for the theoretical yield. And to do that, again, it's going to be a limiting reagent stoichiometry problem. So first steps first here, we do have a balanced equation, so that's all good to go. We need to take what they gave us basically here and convert it into moles. So my moles of TiCl4. Here, though, we are not starting in grams. We are starting in kilograms. So we do have to do an extra conversion there. We want to take our kilograms to grams. So in 1 kilogram, there's 1,000 grams. Kilograms will cancel. That's going to be grams. And now I can use my molar mass like normal here to convert into moles. We'll go 189.7 grams per mole. That's going to give us here a starting moles for our TiCl4 of... Looks like we'll call it 1.3 times 10 to the 5 moles of TiCl4. We're going to do a very similar calculation here for our other reactant, which is the magnesium, also given to you in kilograms. So we do have to do the same conversion there to get it to grams before we use the molar mass. And again, 1 kilogram or 1,000 grams. Kilograms will cancel using the molar mass from the periodic table, which was, if it was not provided for you, you would need to go get. And there it will give us 1.44 to the 4 times 1,000 divided by 2431. Looks like 5.92 times 10 to the 5 moles of magnesium. These again are our starting amounts of each of these guys. Any questions on there so far? Now that we have them into moles, before we can really continue on with sort of the stoichiometry part of the calculation, here's the part where we can determine which one is the limiting reagent. And here I'm going to do my limiting reagent calculation. And in my case, I'm just going to figure out how much, I don't know, it don't really matter, how much magnesium is needed. So in that case, what I'm trying to figure out is how much magnesium is needed to basically use up all my TiCl4. So I'm going to start with my TiCl4, which is 1.3 times 10 to the 5 moles. I'm going to now do the mole-to-mole relationship between the two reactants from the equation. So from the equation, we see 1 mole of TiCl4 gets us 2 moles of magnesium. The moles will cancel. We're going to take 1.3 to the 5th, and we're going to times it by 2. That means that we would need 2.60 times 10 to the 5 moles of magnesium is needed. Remember that we want to take this number and compare it to basically what we are starting with. And I actually only need 2.6 and I have 5.92, so I have enough is basically what that tells me. And because I have enough, what that tells me in this particular case, the magnesium is my excess reagent. The TiCl4 is my limiting. So this guy is my limiting reagent, and this guy is my excess reagent. Any questions on that there? Now that I've determined my limiting reagent, really at this point, I again want to come back here to my starting amounts of the limiting reagent. And I really want to pick up with really the third part of the calculation, which is now I'm going to go from my limiting reagent to my product, which I'm interested in. So to do that, we will take our starting moles, which is important. So we're going to take our starting moles of our limiting reagent, 1.3 times 10 to the minus 5 moles. We will now do the mole-to-mole relationship from the equation, and that is 1 mole of TiCl4 gets me 1 mole of Ti. Once again, you could get an answer at this point, but I'm just going to continue on with the calculation and do the last step or one of the last steps, which is I want to now convert that into grams. So I'm going to use the molar mass from the periodic table, TI. Here I do want grams to go up on top, 4788 grams per mole. The moles will cancel. Actually, in this case, I actually want my final answer to be in, like it asks for kilograms, right? Because my actual yield's in kilograms. So I'm actually going to do one more part of the calculation, which is if I got an answer at this point, I would be in grams. But I'm going to do my grams to kilograms here so that I have it in the correct units. And that'll give me our 1,000 grams as a kilogram. So 1.3 to the fifth, that's positive 5. Sorry, no negative there. Get rid of that there. There we go. Times 4788 divided by 1,000. And that's going to get me here 6.22 times 10 to the 3 here, I think. Let me double check here real quick. 1.3 to the fifth times 47.8 divided by 1,000. There you go. Kilograms here. There you go. And that would be my theoretical yield. There we go. And that is of TI. That is good because I was looking at the wrong number. So that does make sense. That is my actual yield there, which is also to the 3. So that's my theoretical. All right. So my percent yield in this case would be my actual, which was given to us at 5.42 times 10 to the 3 kilograms, divided by 6.22 times 10 to the 3 kilograms times 100%. As I mentioned last time, the units here don't really matter as long as they're really the same. So as you can see here, we could do kilograms, kilograms, grams, grams on top and bottom. It could do moles and moles when you're calculating percent yield, as long as they are in the same units. So we'll go 5.42 to the third divided by 6.22 to the third times it by 100. Gonna get us there about 87 point, we'll call it 14% yield. Not too bad, not too shabby. Again, it really is, as if you look at it, our same sort of 4 steps. Step 1, balance equation. Step 2, convert to moles. We just need to do this limiting reagent calculation. And then this would be step 3, mole to mole relationship. And step 4, basically convert it to some other units. Any questions on that there? Yeah. You got what now? It may be with rounding and stuff. I would assume that's maybe the difference and stuff. So just maybe didn't round or rounded a little slightly different, I would think. Yeah. As long as you have like the 87 in the front, you probably just a little bit of rounding there. Yeah. Other questions? All right. Any questions on stoichiometry, limiting reagents, percent yield, how to do it? Okay. That wraps up this chapter. We're off to gases. In this chapter here, we're going to talk officially about gases. Gases obviously are the state of matter where we have basically everybody flying around freely from each other. As they're flying around, there are collisions that occur. As these collisions occur, for example, with the walls of the container, that's what we associate pressure with our gases. And when we talk about gases, there's usually 3 sort of variables that we talk about a lot: pressure, volume, and temperature. So these are 3 very common sort of variables that we see, especially with the different gas laws. And in some cases, we may hold one of those constant, and in the other cases, we may actually just be changing everything along the way. So a reminder that substances that exist as gases under sort of normal conditions, pressures and temperatures, and when we talk about sort of everyday conditions of pressures and temperatures, that is usually 1 atm, which is an atmosphere, again, a unit of pressure, and basically 25 degrees Celsius. So as you go through chemistry, you'll look up values in tables and stuff like that. That's sort of the standard conditions for normal conditions of every day of 25 degrees Celsius and 1 atmosphere. Now, under normal conditions like those, we typically do not find ionic compounds in the gas phase, and that's because they are held together by probably one of the strongest attractions you could have, which is that electrostatic attraction. The opposites attract between the positive and negative ions, which holds that together. And what typically happens is because of that really strong, what's known as an intramolecular force that holds that together, you could pretty much heat the heck out of that thing, an ionic compound, and it pretty much will not go into the gas phase. It will basically start to melt before it will actually jump into the gas phase because it's held together really, really tight. Now, different than that is molecular compounds, which are again compounds that are basically held together the one compound by sharing of electrons. And those compounds are very different. There are certain ones that are just gases off the bat there. It's like carbon monoxide, carbon dioxide, hydrogen chloride gas, ammonia, and CH4 is methane, which is the simplest organic molecule you have, is the gas that comes out when you light your Bunsen burner there in the laboratory. They are gases at sort of room temperature. But a majority of molecular compounds are actually liquids or solids at room temperature. The major difference between, say, molecular compounds and ionic compounds are it is much, much easier to convert a molecular compound into the gas phase than it is, say, an ionic compound. Probably the most common example of that is our friend water. And water is very easily turned into a gas by simply heating it up to about 100 degrees Celsius, and it becomes steam, which is basically water in the gas phase. So the reason that is really easier to do than, say, an ionic compound is water, as we know, is a polar molecule, where the oxygen is more negative, the hydrogens are really more positive side of it. So what holds one water molecule together with another is what is known as an intermolecular force. And that particular intermolecular force is opposites attract. That is what is known as hydrogen bonding. And hydrogen bonding, although it is a relatively strong intermolecular force, and an intermolecular force is basically the force that holds one molecule together with another. So basically two water molecules, for example, is the force that holds those two water molecules together. That's different than a intramolecular force, which is within the molecule. So if you just took one water molecule, the covalent bonding that's holding the oxygen and hydrogen together on one side, the sharing of electrons, and also sharing electrons on the other side, that's what's known as an intramolecular force. And intramolecular forces, like you have in ionic compounds, which is that electrostatic attraction, is always much, much stronger than an intermolecular force, even though the intermolecular force may be relatively strong to begin with. And what that means is when you go to heat something that has water in it, because the force that holds this water molecule together with this water molecule is weaker than the individual bonds in every water molecule, what actually breaks first when you heat it is that bond between the two different water molecules. And what that allows is for this water molecule to go off into the gas phase and this guy to go off into the gas phase as intact water molecules that basically just separate from each other. If that was different, for example, and the intramolecular force was weaker, what would happen when you go to boil water for making pasta is you would break apart all the water molecules into hydrogen gas and oxygen gas, which, as we've seen, is kind of flammable and not so great. So you probably wouldn't get to the pasta making part because everything would come apart as hydrogen gas and oxygen gas. It doesn't do that because, again, this intermolecular force is weaker So when you heat it up, you actually just get water molecules that break apart and make steam as it starts to boil. So the general rule is the less attraction force that there is between molecules, the less or weaker intermolecular force, the more likely that thing will exist as a gas. Now, something like methane, which is CH4, that's a nonpolar molecule. And because that's nonpolar, what it uses for intermolecular forces is what's known as dispersion forces. And dispersion forces are pretty much the weakest type of intermolecular force you could have. It's like the weakest attraction between two molecules that you could have, that pretty much, if you just look at it wrong, they're just going to kind of break apart and go away from each other. And that's why a lot of, for example, organic molecules, which are nonpolar, typically are very volatile or can go into the gas phase really easily, because they're not held together by really strong forces. So it doesn't take a lot for them to separate out from each other and basically just go off into the gas phase and break apart from one another. So what are some substances that under normal conditions are found as gases? We have our diatomic elements like our hydrogen, nitrogen, oxygen, fluorine, and chlorine. Those are all gases. They are all diatomic molecules. Again, they come as twos. Ozone is a gas. And then, of course, we have group 8 on the periodic table, which is our noble gases. And those guys come as monoatomic, which means they essentially come as one. So those guys are typically our gases under normal conditions. So you can kind of see our hydrogen, and then everybody kind of over here under normal conditions are going to be your gases. So this is also a good time to talk about a difference between two words that are sometimes used interchangeably with gases, but they really probably shouldn't. One is a gas, and a gas is a substance that normally would be in the gas phase under normal conditions. Now, a vapor, on the other hand, is a substance that is normally either a liquid or a solid under normal conditions, but you have converted into a gas. So that's why, for example, when we talk about water, we refer to it sometimes as water vapor rather than water gas, because it just sounds funny, water gas, but because water is not normally found in the gas state, but you can convert it into the gas state, and that's why it's referred to as water vapor. That's why you looked up the vapor pressure of water the other day, right? Because that's basically water in its gas state. So when we talk about the pressure of gases, we live at the bottom of the ocean, whose air is basically mostly, by the way, composed of nitrogen gas is the major component of air, followed by oxygen, which is next, plus other gases depending on what air you're breathing in and where you're standing, I suppose, up the pine. The density of air decreases rapidly as you increase the distance from Earth. And one of the most measurable properties of a gas is pressure. And again, that's usually what we associate with gases, usually what we follow, for example, in calculations, if we're dealing with a gas, a lot of times is the pressure associated with it. Now, it is related to the number of collisions. So just a very simple explanation is, as I mentioned before, if there are more collisions, then there's going to be a lot more pressure. And if you have a lot less collisions occurring, you will have a lot less pressure occurring. Now, one way that we measure pressure is through a barometer. And a barometer is an instrument that measures atmospheric pressure. And they were not always digital like we have in the lab, but they mostly were a traditional barometer, basically a glass tube that's submerged in some mercury. And as the atmospheric pressure exerts down on the mercury in the tube goes up, and the mercury rises there in the tube. And that gives us some very common units of pressure. An ATM is an atmosphere, and I would say that's probably the most common unit of pressure, for the reason of, in most calculations, or in a lot of calculations, you oftentimes will need the pressure in atmospheres, and that's a common sort of unit. Other common units is a torr, named after Torricelli here, who invented the barometer, and mmHg, which stands for millimeters of mercury, and that is because on most traditional barometers, there's frankly a ruler on the side of it, and you can measure the height of the barometer in the column. And by the way, mercury, or you can measure the height of the mercury in the column there. And by the way, mercury is one of those weird ones that the meniscus actually goes the opposite way. You would actually read from the top of the meniscus if you see a mercury barometer. And you would measure it in inches of mercury, or centimeters of mercury, or millimeters of mercury, basically, is what that stands for. 1 torr, though, is equal to 1 millimeter of mercury. It's basically a 1-to-1 conversion. So if you have to convert between those units, you basically just change the unit. The number stays the same. But that 760, which is what 1 atmosphere equals in millimeters of mercury or torr. So 1 atmosphere equals 760 millimeters of mercury or 760 torr. That number is an important number because out of the many units of pressure, which by the way, there are units of pascals, kilopascals, bar, psi. There's lots of units of pressure, but these are pretty much the big three in chemistry: atmospheres, millimeters of mercury, and torr. 1 atmosphere is equal to 760 millimeters of mercury and 760 torr. So basically, if you have atmospheres and you want either millimeters of mercury or torr, you're going to multiply by the 760, and that way the atmospheres will cancel, gives you millimeters of mercury or torr. Or if you have millimeters of mercury or really torr, you're going to divide by the 760. And that equals an atmosphere, and that will give you atmospheres. So that 760 number is an important one. It is really your conversion factor to go between those different units. Here's a much nicer picture of a barometer, and as you can see there, we have our mercury going upwards in terms of its meniscus. And like I said before, typically on this glass tube here, there's some type of ruler where you would take a measurement in either millimeters, centimeters, or most of the time it used to be inches of mercury. A lot of them would be what you would measure. Now, as I mentioned before, some other sort of units that, in terms of pressure, that we don't see too often necessarily in chemistry, but occasionally they do pop up. Again, a pascal is a common unit of pressure. 1 atmosphere is 101,000 or so pascals, or 101.3 kilopascals. PSI, which is pounds per square inch, that's 14.7 PSI is equal to 1 atmosphere. And lastly, a bar, sometimes you see 1.01 bar is equal to 1 atmosphere. So those are some other common units of pressure: PSI, bar, and pascals or kilopascals that you do sometimes come across. But again, I would say probably the big three going to be the atmospheres, millimeters of mercury, and torr. I would say most of the time those are probably going to be the ones that you are going to come across. All right, so as I talked about before, there's really 3 variables that we talk about with gases: pressure, volume, and temperature. And there's a bunch of gas laws that we're going to learn about some of the relationships that occur. And the first one is going to be Boyles Law. And Boyle basically studied the relationship between pressure and volume. And with Boyle's Law, we held temperature constant. So temperature is held constant here with Boyle's Law. And what we found was, or what he found in terms of the pressure volume relationship, is as the volume increased, the pressure went down. So if you think about it, if the volume increases, you're now giving these gas molecules a lot more room to fly around it. And because they have a much larger volume, there's much more room for them to fly around it. And that's going to mean we're going to actually have less collisions occurring because it takes longer for everything to find each other. And because the collisions would go down, we see a decrease in the pressure. Now, what he found though is if you drop down the volume, you decrease the volume, you now have all these gas molecules in a much smaller sort of area. And what that's going to cause is there's bound to be a lot more collisions occurring because, frankly, they don't have to travel that far to hit the walls of the container or anything else that's flying around in there. And what that's going to do is increase the number of collisions. And what you'll see is the pressure will actually go up. So Boyle's relationship is basically is inversely proportional to the gas pressure, the volume. As one goes up, basically the other goes down. Another kind of interesting thing that happens with Boyle's law is if you study a gas over a variety of pressure and volume relationships, and you multiply those pressure and volume numbers that you get for that same gas, it will always end up being the same number, which is known as a proportionality constant. So you could take a gas and study it at many different pressure and volume sort of relationships, and if you multiply them together, they're always equal to the same number. And because of that relationship that they equal basically the same number, you could actually set up a gas law like we have with Boyle's law, which is P1 V1 equals P2 V2, because frankly, they both equal the same number, so you can set them equal to each other. This is kind of like a before and after situation here. This again is at constant temperature. Now, in terms of the pressure on both sides, it does not matter the units as long as they are the same units on both sides. So everything cancels. So they could both be atmospheres, for example. They could both be millimeters of mercury. They could both be torr. But you cannot have one side like atmospheres and one side torr because your calculation will be incorrect. So they do have to be the same unit. Volume here also on both sides does not matter the units. Once again, though, they do need to be the same units. Otherwise, again, you're going to be off. So you can't have milliliters on one side and liters on the other. You can choose, honestly, whichever one you want to convert to, but they do need to be the same. So we could use this relationship basically to see what happens if we change the pressure, we change a volume in a constant temperature situation. And here's a graph of Boyle's relationship. And as we can see here, at lower volumes, much higher pressures. At larger volumes, much lower pressures that we see going on basically over here. And again, it just gives everybody a lot more room to fly around in. That's going to lower the number of collisions. But when you lower that sort of volume, you kind of squish everybody together, going to cause a lot more collisions occurring. And that's going to be a lot more pressure. So let's try one here. An inflated balloon has a volume of 0.55 liters at sea level, which is 1 atmosphere. It rises to 6.5 kilometers where the pressure is 0.4 atmospheres. Assuming the temperature remains constant, what will be the final volume of the balloon? Okay, so let's take a look at this. And I would recommend, usually when you do sort of gas law problems, a really good way to sort of do them is to pull out the information from the problem, kind of label what it is as a pressure, a volume, a temperature. And a lot of times it will really direct you to sort of the correct gas law to use. Obviously, in this case, we only have one to choose from, which is P1 V1 equals P2 V2. But if we go through the problem, we do have a volume that is 0.55 liters. 1 atmosphere is a pressure. 6.5 kilometers is useless information in this problem. Pressure here, 0.4 atmospheres, and we are looking for a final volume. So we could call the first stuff in the problem the ones, the second ones the twos, and we could see in this case that we basically just need to solve for V2. We could also see that probably Boyle's law here would be the right gas law to choose as it got 2 pressures, 2 volumes. You could kind of almost see Boyle's law in sort of the numbers there. So in this case, we are going to divide this to the other side. And by the way, in gas laws, when you move something to the other side of the equal sign, it ends up on the bottom or opposite location, not really opposite location of where it started from. So putting in our numbers here, we got our P1, which is 1 atmosphere, our V1, which is 0.55 liters, and our P2. In this case, both of our pressures were in atmosphere, so that is really good because they do cancel. Again, if they were not in the same unit, you would need to do a conversion, and that's going to get us there. We'll call it a 1.4 liters in this case. And by understanding the Boyles Law relationship, we could make sure, our answer does make sense. What we see here when we look at the pressures is from the first pressure to the second pressure. Pressure went down, which means the volume should go up. And it started at 0.55 liters, ended at 1.4. So we do see the relationship that we would expect in Boyles Law. With that pressure dropping, we do see here an increase in the volume. So that's one way you could sometimes check your calculations to make sure you didn't reverse a number or something like that, or put a number in the wrong spot, which is, again, a very common sort of mistake. Any questions on that there? All right. All right, here. Let's talk about another couple of gas laws, and this is Charles' law and Gay-Lussac's law. And Charles' law dealt with the volume and temperature relationship, holding pressure constant. And really, Gay-Lussac's law dealt with pressure and temperature and held volume constant. So when we look at these relationships, we can sort of figure out what might happen here. So if we look at like Charles' law, that's going to be a V1 over T1 equals V2 over T2. And this, again, is at constant pressure. If we look at more Gay-Lussac's law, it's going to be a P1 T1 equals P2 T2. And again, this is at constant volume. So if we just think about the situation on the right-hand side, if I have a constant volume in a rigid container, volume's not going to be able to move, and I have gas molecules in there. If I increase the temperature in this situation, my gas molecules should start to fly around a lot faster. So I'm going to have gas molecules in here flying around a lot faster, and that's going to cause a lot more collisions to occur. And because that's going to cause a lot more collisions to occur, what we should see in that case is an increase in the pressure because they're flying around faster, a lot more collisions basically occurring. Now, again, if I have a fixed volume and my gas molecules in there, and I decide to lower the temperature, when I lower the temperature, what's going to happen to my gas molecules are they're going to fly around a lot slower because they have a lot less energy. And that means that as they're flying around a lot slower, dramatic slower drawing there, is going to be a lot less collisions occurring. And because we'll have a lot less collisions because everybody's moving around a lot slower, we will actually see the pressure start to drop here. So the relationship that we see in sort of Gay-Lussac's law, because the volume is basically fixed, it can't move, we will actually see the pressure go up as the temperature goes up, and we will see the pressure start to come down as the temperature comes down with it. Now, that's different than what we actually see here in Charles' law, because in Charles' law, the goal of it is we want to keep the pressure constant. So what happens in a Charles' law situation is if you have some gas molecules and you decide to increase the temperature, what's going to happen is pretty much as we see on the right-hand side there, if the volume doesn't move, we will see the pressure start to increase. So the way that it's able to actually keep the pressure constant is we actually get a adjustment in the volume. So even though they are flying around faster, they now have a lot more place to fly around in. And what that's going to essentially do is because the volume adjusts, which you could do with like a movable piston, you could go up and down and kind of adjust the volume. That will allow the number of collisions basically to remain constant and the pressure to remain constant. So in Charles' law, as the temperature increases, to allow it to maintain constant pressure, the volume will actually adjust of the container, for example, and that will allow the number of collisions, even though they're moving faster, to still remain the same, and that's what keeps it basically at constant pressure. Opposite will happen as well if you have some gas molecules in there and you lower the temperature. Once again here, if the volume just stays, what we would have is what we have on the right there. When you lower the temperature, we have people moving slower, less collisions, and we're going to see a drop in pressure. So the way it's able to maintain that constant pressure is the opposite effect happens. It actually lowers the volume. And by lowering the volume, what that's going to do is put all the gas molecules much closer together in a much smaller area. And even though they're flying around slower, they don't have as far to go to cause collisions. And that will keep the number of collisions constant. And we will actually see the volume decrease. So with Charles' law, as the temperature goes up, so does the volume. And as the temperature goes down, so does the volume. Any questions on any of those relationships there? Now, when we look at sort of the, go back to this in just a second here. When we look at the Charles law relationship, and if you graph the volume versus the temperature in Celsius for any gas you like, any of these gases or any one you choose, and if you extend the line back to the temperature axis for all those lines, they all hit at the exact same spot. They all hit at minus 273.15 degrees Celsius. That number should look familiar to you because that's the number we use to convert to what? Kelvin. Yeah, because if I add 273.15 to it, I have 0 Kelvin, or absolute zero. So obviously Kelvin recognized the relationship of this, and that's why it used to be called the absolute temperature scale, but later renamed Kelvin for him. And basically what that means is pretty much any gas law that you come across, the temperature always has to be in Kelvin. So temperature always needs to be converted to Kelvin. So when we look at our two that we just looked at, our Charles, V1 over T1 equals V2 over T2 here for our Charles. The temperatures here need to be in Kelvin always. Now the volumes, it doesn't matter. The volumes can be this whatever unit you want as long as they are the same. That also means that sometimes people come across problems and they think logically that they are given the temperature in Celsius and they're asked to give the answer in Celsius, so they figure I could just leave it in Celsius. And you will get the wrong answer. So regardless if they give you the temperature in Celsius, they want the answer in Celsius, you do have to convert it to Kelvin, put it into the gas law, and then convert it from Kelvin to Celsius. So it's always got to go to Kelvin before it goes into any gas law. If you're doing anything that involves a gas law and then temperature, if you're not putting it in Celsius, you're going to get the answer wrong. It should pretty much be a no-brainer. If you got temperature or gas law, just should be like the first thing you do. Just convert it over to Kelvin and you'll be okay. And the same thing with our Gay-Lussac's law here, same deal. Our temperature here does need to be in Kelvin. And in terms of our pressure, same as the volumes, it doesn't really matter as long as they are the same on both sides. Any questions on that there? All right. So that's what we basically just talked about. Also, by the way, if you take volume divided by temperature, it will equal a proportionality constant. And that's why we could set up these two relationships that we talked about here. All right. All right, so let's take a look at a problem here. I think there's our other guy. In an experiment, 452 milliliters of a gas is used in a light bulb. It's heated from 22 degrees Celsius to 187 degrees Celsius. What is the final volume? Let's see what you come up with here. Look, so again, like I said, if you sort of pull out the information, we definitely have a volume of 452 milliliters. We have a temperature 22 degrees Celsius and another temperature at 187 degrees Celsius. And we are looking for a volume. So if you just think about the gas laws we got no pressure, so that eliminates that guy. We got no pressure, so that eliminates that one. And it looks like Charles' law is our guess, and you can kind of see even Charles' law there by just writing it out. You call the first set of information ones and the other ones twos. Really doesn't matter which ones you call ones or twos, as long as you keep the numbers that go together together. Like normal, as I mentioned, we're going to just automatically take our temperatures to Kelvin because we know we're dealing with gas laws, so they need to be converted. So we'll do a 22 plus a 273.15, going to give us a 295.15 Kelvin. We'll do a 187 plus a 273.15, going to give us a 460.15 Kelvin. Here we have V1, T1 equals V2, T2. We want to solve for V2. As I mentioned before, when you move something across the equal sign in gas laws, they end up in the opposite location. So T2 is on the bottom. When it goes across, it's going to basically end up on top, opposite location. That's because we're basically multiplying it to both sides there. And that's where we'll end up. So that'll give us T2 V1 T1 equals V2. Popping in our numbers correctly here. T2 up on top, 460.15 Kelvin, V1 452, and divided by 295.15. Kelvins are going to cancel. That's going to leave us milliliters for our units. So that's going to be a 460.15 times a 452 divided by a 295.15. Going to get us about a 705 milliliters in this particular case. So when we look at this, we could see what happened. Our temperature went up in this relationship. So we would expect our volume to go up, and it went from 452 to 705. So again, it matches what we would expect to happen in this Charles law relationship. Any questions on that one there? All right, so continuing on here. Let's talk about our friend Avogadro. Avogadro had a number, but he wanted a gas law, so why not? So there's Avogadro's law. And when we think about Avogadro, we really do think about hopefully 1 mole, right? Equals 6.022 times 10 to the 23. So not surprisingly enough, his gas law involves moles, and that's what the N stands for here. These are moles of gas. V is obviously volume. Avogadro's law is actually under 2 conditions, and that is basically constant pressure and temperature. So for Avogadro's law to be in place, you have to have constant pressure and temperature involved. And basically the relationship for Avogadro's law is this. If you have constant pressure and temperature, basically there's a direct proportion to the volume and the number of moles of gases. So as the moles go up, so there's sort of the volume as well. In fact, you could use Avogadro's relationship, for example, to do stoichiometry problems. So if you had this plus this goes to this, and this was under constant pressure and temperature conditions, like we could do a mole to mole relationship, like 2 moles of A is 1 mole of B, could actually do a volume to volume relationship between those things. You could say 2 liters of A would equal 1 liter of B. So because it's under these conditions, Avogadro's law applies, and really sort of as the moles go up, so does the volume and vice versa. And it actually is kind of helpful sometimes when you're doing gas stoichiometry problems if you're under these conditions. You can just roll straight from volume to volume relationships instead of having to maybe use a gas law to solve it. You could actually just kind of solve it like that. We'll see maybe an example of that a little bit later. Now, All right, now we can take a look at it. So if we had something like this and Avogadro's law and stoichiometry, and we had it at constant temperature and pressure, if we were to figure out or want to know if we started with, say, 4 liters of N2, and we want to know how many liters of NH3 would we produce. Basically, because this is at constant temperature pressure, like I just mentioned a second ago, we pretty much can do a stoichiometry problem involving volume because these are all gases. So we would do a similar one. We could look at this and go, okay, that is 1 liter of N2 would give us 2 liters of NH3. And that's the same thing as we would do if we looked at it and said 1 mole of N2 gives us 2 moles of NH3. So in this case, we could very simply solve this problem by taking 4 liters of N2, just do really a volume to volume relationship here from the equation. 1 liter of N2 gives us 2 liters of NH3. Liters of N2 would cancel, and we would end up with 8 liters of NH3. So this is like an added benefit of sort of Avogadro's law, which is you can do a stoichiometry problem without actually having to use a gas law to solve it by just simply using that volume to volume relationship. You could obviously do it liters to liters like I did here, or whatever unit you want, just like you would do sort of a mole to mole relationship. Any questions on that there? All right. As we'll also talk about later on in this chapter, you could also use a gas law and do the same thing, and you'll get the same answer. Now, if we take all those gas laws together, Boyles, Charles, Avogadro, we get the granddaddy of them all, which is the ideal gas law, which is PV equals nRT. So PV equals nRT is the ideal gas law. It's different than all the gas laws we've seen up until this point because there is no 2 conditions. It's like a one and done condition. You got 1 pressure, you got 1 volume, you got 1 temperature, 1 moles. You don't got 2 of everything. What's an ideal gas? What makes something an ideal gas is really kind of 2 things that we'll talk about. But essentially, one thing that makes something an ideal gas is under ideal conditions, it is actually more important the volume of the container that the gas is in than the volume of the gas itself. So if you think about a lot of examples we did, or the problems that you will see, they oftentimes talk about the volume of the container the gas is in. And under an ideal situation, we assume they're flying around uniformly in that container, and the volume of the container is much larger than the volume of the gas itself. So under ideal conditions, we actually don't even look at the volume of the gas itself. It's negligible. The second thing that makes something an ideal gas, which comes into play when we talk about mixtures of gases, is the idea that under ideal conditions, even though you may have multiple gases in the same container, there is no interaction between those gases. So there's no attractive forces between gases. There's no repulsion forces between gases. So even if you had a mixture of 2 different gases in the same container, under ideal conditions, you basically just assume that each gas is in there by themselves because the other gases in there will have no effect on the other gas. And when we look at the ideal gas law, it is also the most restrictive in terms of units. So when you use the ideal gas law, the pressure has to be in atmospheres when you use it. The volume has to be in liters when you use it. N is moles, so that should be moles. And T is Kelvin. And again, the reason why all those guys has to be in those units is the value of the gas constant, 0.08206. Liters times atmosphere, Kelvin times mole. So in order for all those other guys to cancel out correctly in terms of their units, that is pretty much the units everybody has to be in, which means if you can remember the units for the gas constant, you know what all the units has to be for everybody else in the ideal gas law. Any questions on that there? Now, a couple other important relationships that we actually see with the ideal gas law is we'll start with STP. As we talked about the other day, STP stands for standard temperature and pressure. And essentially, when you're given STP, it actually is giving you a value for temperature, and that value is 273.15 Kelvin. And it's giving you a value for pressure, which is basically 1 atmosphere. So if you're doing a calculation that involves the ideal gas law, you basically would put in for pressure 1 atmosphere, you would put in for temperature 273.15, or anytime you use STP, that's basically what it means. Now, if you happen to be at STP conditions and only at STP conditions, you could actually use a relationship like we used in the lab last week, which is if you are at STP conditions, 1 mole of any gas will equal 22.414 liters. So that is a conversion. Again, you do have to be at STP conditions to use. And what that will allow you to do is, frankly, not have to use the ideal gas law. If you're at STP conditions, you could just, frankly, use that conversion and get the answer. Now, if you don't want to worry about that conversion, because you guys have a lot of things to remember in this class, you could just throw it away and always go into the ideal gas law. You don't have to ever use that conversion. You can just put everything into the ideal gas law. You could use the ideal gas law pretty much in any condition. You use it for STP conditions, non-STP conditions. You could always just go into the ideal gas law. You get the same answer. So if you want to use that conversion, though, it has to be at STP conditions. If the temperature is not 273.15 and the pressure is not 1 atmosphere, you should never use that conversion. You can only use it under those conditions. So that's what I was saying. If you don't want us to worry about it, just forget it and just pop it into the ideal gas law always and just use the ideal gas law and you'll be okay by putting the numbers in. By the way, if you do put the numbers into the ideal gas law and solve for R, that is, by the way, how we do get the gas constant there, 0.08206, because the pressure would be 1 atmosphere, the volume would be 22.414, 1 mole, and the temperature would be 273. Any questions on that there? I'm going to try one here to wrap it up. Calculate the pressure in atmospheres exerted by 1.82 moles of SF6 gas at 5.43 liters and 69.5 degrees Celsius. Okay, so since we're getting to the end, let's take a look. We're looking for the pressure. They definitely give us moles of 1.82 moles. We do have a volume that's 5.43 liters, and we do have a temperature here of 69.5 degrees Celsius. Again, you can see I don't have 2 pressures. I have no 2 volumes. I have no 2 pressures, no 2 volumes. So that basically leaves us the ideal gas law is the only gas law that makes sense. You always have R, and by the way, it is never given to you in a problem. They just assume you know that number. So you always basically have that number available to you. But like I said, they very rarely ever give it to you. We do need to, like normal, just convert our temperature into Kelvin, and we'll go 342.5 Kelvin. Our volumes in liters, so that's good to go. And obviously our moles here is in moles. So PV equals nRT. We're going to divide our volume to the other side. Gives us P is equal to nRT divided by V. So we will have here basically our moles of 1.82 moles, our 0.08206 liters atmosphere Kelvin mole, our temperature in Kelvin 342.1 or 0.15, I think, right? 342.5 Kelvin, and our volume of 5.43 liters. Moles will cancel, Kelvin will cancel, liters will cancel, leaves us atmosphere. That's the only unit left, 1.82 times 0.08206 times 342.5 divided by 5.43. Going to give us a pressure of 9.42 atmospheres. Question on that. Now, other things that you sometimes need to do with gas laws is a lot of times you're given things in grams, so molar mass to convert to moles. Also, volume, a lot of times are in milliliters that you need to convert to liters. So those kind of 1,000 milliliters of the liter are using the molar mass to go from grams to moles are common conversions you also have to do with this. Any questions on